Hey guys, I'm so sorry for making you wait all the way till today. Like just to go through the experiment. It's actually like my first time after like the whole week to actually get on Zoom and start any recording or like reaching out and do my TA responsibility. So I'm so sorry and thanks a lot for your understanding, especially those that have sent me some really sweet messages and kept me in your prayers. Like I sincerely thank all of you like for your understanding. Okay? Alright. Um so because I'm starting this experiment so late in the week, I would just like you guys take all the time you need. Like even for the cobalt chloride, if you need to revise anything, like I actually have not even checked the messages. I will check all the messages and the emails tonight and respond to you like within the day, like within today. And if you need any other revision, like feel free to just work on it and send back to me. Like um I still had to grade your first lab report, so it's fine if you need some time and work on your experiment. Like, at least for me, like I don't put that much of a big deal on deadline. So like, if you need time to make your work perfect, then like by all means do that. Like just as long as you don't wait all the way to the end of the term, then I'm fine with that. Um, So for this week, we'll be working on the indicators. So indicators are actually weak acid and weak base. Um, so depending on the pH of your solution, like it would change to corresponding colors. Like so the acid form would have a different color and the basic form would have a different one. So like you can actually look at the range of color of each indicator and can tell like the pH of either your solids or like your entire solution. So I have taken some notes, and if you guys want to, I can send a message of these notes if they can help direct you through the experiment. Yeah. Okay, so let me start sharing that with you. Screen. Nope, I'll share this one. Actually, no, let me start sharing the whole screen. All right. Okay, cool. So that's the Zoom. I hope you are all looking at the PDF file I'm pulling up right here. So like these literally are just what I downloaded from your lab canvas and printed out so that I could do the work. But you can always go back and search for the link to these scale of indicator colors. Yep. So like these are the 3 pictures that I found pretty helpful like throughout the first 2 parts of your experiment. Um, yeah. Feel free to use whichever scale of pH indicator that you guys want to. But here, let me just start jumping into the very first part of the data collection. So like this is the first table you guys have to fill out. Like it literally is just you looking at this very first picture. So the stockroom people have done us like such a big favor and tested 7 indicators across like pH 1 to pH 12. So like all you have to do is to spot a change in color. So for example, this one would be methyl orange, I think. No, methyl violet. Yep, methyl violet. And like the very first change in color would be between pH 1 and pH 2. So like all you have to do would just be to spot the change in the color like across the entire scale from pH 1 to 12. Yep, so for example, in methyl orange, my picture is very is not that distinguishable between different colors, but like you can always go back to the lab picture and pull up this picture. That should be a change in color around pH 5. So like right there. Yep. So I have also done like an answer key for myself. So for example, I made a pH scale. So when you go from methyl violet all the way to alizarin yellow, the pH would increase from very acidic to super basic. And your next job would just be to write down like what is the range of pH you are perceiving for a color change. So for example, methyl violet should be around pH 1 and 2. So you can just write down pH 1 to 2. Same for like the other 6 indicators. And then to find the constant, the indicator's equilibrium constant, KIN, it will just be KIN equals to 10 to the negative of pH. So I made a calculation, but it's not on this picture, but this is like just for simplicity, like you just have to replace the value that you were putting in for the transition range and then put it into your KIN in order to find the equilibrium constant. Yep. So that's the very first task you have to do. I was putting like my own like annotation right here, like see picture 1, 2, 3. So this is my own like kind of annotated code. Like that would be picture 1 and then 2. And for some reason I have like a blank page, but yeah, picture 3 would be over here. Yeah, but that's just to show you where you can find the information in order to put into your data table. So going over to the second table, this one, like, I know it looks pretty confusing at first, but literally what it means is to have you look at another set of data. So the starting people have done is like, oh my god, a really good favor, a really nice favor this time. So they tested each salt over like 6 to 7 types of indicators. So like what I did when I filled out this table was literally to like put this picture right below the whole scale of colors over here, and then just pick out whichever pH would match the best with the entire range of colors. So for example, like NaCl, it would be an orange color for methyl orange, but like excuse me, but like for all the other indicators, it's gonna be yellow. And then what is that? Can't read it. Phenolphthalein would give like a clear color still to NaCl. So let's go back to this picture. Rotate it. Yep. So like that. So like if everything is actually around yellow and like there's only one clear spot and like it would return to the yellow color again. So like immediately it would tell you that okay, NaCl has to have a pH of less than 8 in order to have a clear color. So what I noted down on my notes was that it looks like it's around pH 6 because because of the slight change in the color, like in the hues of orange between like the second and the fifth indicator. Hopefully it makes sense. Right here. So you can see that it's pretty orange at the very first spot, and then like there would be 3 other spots that would be in yellow. So I put down the color that I was seeing, and then like I would highlight a specific indicator that gives me a very big hint of whichever pH the salt is supposed to be. So like I can't I actually will post this one if it helps you guys compare your answer to. But like it's more of like a work I was doing. So like if you find a mistake, then just let me know. Like don't think that this is like the supreme recipe. Just let me know. Okay. All right. So you just have to fill out what color you saw for each of the salts using this picture, these pictures that the Stockholm people made for you, and then go back to the range of color and determine what pH you think is corresponding to all these colors of the indicators for each of your salts. So after you get the pH down, just calculate your hydronium concentration using the negative log of H plus concentration equals pH. So concentration of H plus would be 10 to the power of negative pH. That was it. And then KOH would be, actually, let me see if I can add some notes and write to you guys. Add notes. Can I write something? Oh, that doesn't help. Okay. So it doesn't help, guys. Okay, hold on. Let me try because I don't want to leave you guys clueless of what you should be doing. Okay. All right. So H plus concentration should be 10 to the negative pH. Oh yeah, that's sweet. I actually do not have enough space. Am I supposed to do this so that we can move on and you guys can see the notes better? Okay, so that one should be 10 to the negative of pH. Okay. And then this one should be 10 to the negative 14 divided by the concentration of pH plus. That would just be it. Yep. So I made a table if you guys want to compare. And then this one is a small table for the carbonate water. So Roger was able to show you the color of like the two solutions of carbonated water. When it's completely at room temperature, you know that like carbon dioxide, oxygen, nitrogen, any kind of gas would be solubilized in water. So like all those tiny gas would contribute to the pH of the water at room temperature. So I put in a chemical equation over here. So carbon dioxide plus H2O would produce bicarbonic acid. Yeah, bicarbonic acid. Yep, and then this one would dissociate into hydronium ion and bicarbonate ion. Yep. So because this one is a weak base and this is a strong acid, like when you have something weak and something strong, the stronger ion would always dominate and give you the final pH for the solution. So if this one is like the only H plus that's present in your solution that is considered a strong ion, then it would make your entire solution acidic. So carbonate water at room temperature would be quite acidic, and indeed it has a red color and it corresponds to a pH of 4. However, when you boil the water, like it would force oxygen, carbon dioxide, or like any solubilized gases to be removed from your water solution. So the entire solution would now be purely water. And water has a pH of 7. That's why now when you test the pH using the indicator, it's going to be green. Like it's going to be 7, neutral. So this is all that you need to fill out for the second data table. I am gonna move on to my notes for the simulation. So okay, so starting with the simulation, um this is what I see. You would just be clicking onto the salts, and then for each pair, I would be assigning 3 salts to each of you. To each pair, not each of you. But yeah, I still have to work on that, and I still have to work on the class spreadsheet as well. But I'm gonna try to send all of that out by tonight. Okay. All right. So for example, I would just be picking on the salts, one that I happen to have worked on randomly. Okay. So ammonium nitrate. Okay, I'll just be clicking on whichever salt that I get assigned, huh? And the volume would be 40. Molarity was assigned to be 0.1 molar, but because you have to click on this bubble, so I'll just have to make it 100 times 10 to the negative 2 to make it 0.1 molar. Okay. Yep, so just that, you click on the salts, you click on the volume, and on the molarity, just have to hit insert probes, and then note down the pH that you are seeing. So I'm seeing 4.62. Yeah, so like this is all you need to do. Let me see what I have to say from the notes. Alright, cool. Just note down the pH for this part. So let me go over to my notes right here for you guys. Yep, so NH4NO3, the pH. This pH is different when I did it. I don't know why it's different. But note down whichever value you see from the simulation. And then the next thing you would have to do is to write a hydrolysis reaction. So when the salt is dissolved in water, the cation and anion will dissociate from each other. So you would be forming an ammonium ion and a nitrate ion. Next, you would be writing two hydrolysis reaction equations for each of the two ions. So NH4 plus would add with H2O in the solution in order to make ammonia, which is a weak base, and hydronium ion, which is a strong ion. Yep. And then nitrate would be combined with H2O in order to make nitric acid and OH minus base. Hold on. So sorry, guys. Right. So the thing is that when you have a strong acid or a strong base in the products of your hydrolysis reaction, it would just be like an immediate no. Like you can just look at that strong acid or strong base and know that this hydrolysis reaction is not right. So you know that there are just 6 strong acids to remember: HCl, HBr, HI, nitric acid, sulfuric acid, and phosphoric acid. The strong base would be any kind of base that would end in OH. So if I have like sodium hydroxide or lithium hydroxide, anything that would end in OH would be a strong base. So because we are seeing a strong acid right here, you know for sure it's going to dissociate into H plus and NO3 minus, and it will not be retaining in this form. That's why you can just like cross out this equation. And the other equation, on the other hand, actually produces a weak base ammonia and then a hydronium ion. So the funny thing about weak bases and weak acids is that they cannot completely dissociate. So when you put them into a water solution, it would flip back and forth between the reactants in the product form, so that like this ammonia form would actually exist instead of completely existing in like two distinguishable species of like a cation and the water. Nope, like weak bases and weak acid would be able to go through equilibrium and exist as the weak form of either a base or like a conjugate base or a conjugate acid. Yep. So because this one is producing a weak base and hydronium ion, you know the entire solution would be acidic. So just to check that, here, yeah, our pH is 4.62, which is acidic. So we are on the right track. All right. The last thing you would have to do for part A would just be to note down whichever ion that is spectator, like that is a spectator ion. So we have two ions, NH4 and NO3 minus. The spectator ion would be NO3 because it doesn't participate in your hydrolysis reaction. And NH4 plus actually makes the solution acidic. So the other ion that doesn't participate would just be that neutral ion. All right. Okay. So moving on to part B. So of the 3 salts that you got assigned, you just have to pick one acidic salt. So it just happened to be lucky that I chose NH4NO3 because it makes the solution acidic. So you just have to rewrite your hydrolysis equation and then make a table of concentration versus pH. So you would have 6 values for concentration. 2 molar, 1.6, go down to 0.40 molar. Yep. So now we just have to go back over to the simulation, change your molarity. Oh, get it. Okay, I understand why. Okay, the molarity that I was putting in at first was like 200 or something. So like it has to be a different molarity in order to give a different pH. But excuse me, like, don't worry too much about it. Okay, so starting with concentration 200, I will actually, nope, I have to remove the probe. Okay, yep, and then 200, and then keep the volume 40 milliliters, and then insert the probe again. Yep, so you just have to do this again and again 6 times across 6 concentrations in order to collect your pH. And next thing would be to use the pH and find the concentration of H plus. So I actually made like a really simple concentration just in case, like I believe that all you have watched the lab lecture recording and have started on the experiment before I can even send out this video. But yeah, I just note down the calculation just in case any of you need it. Yep. So find the concentration of H plus across the 6 values of your salt concentration, and then just think about Le Chatelier's principle and think like, hey, why does your pH increase? Like, why does it get more basic with less concentration of salts that you put into the solution? Yep, just think about it. And then next task would be to find KEQ. So from this equation, the KEQ would always be the multiplication of 2 products divided by a multiplication of 2 reactants. So because our reactants has like H2O in it, and like we never include H2O in the liquid form into any equation in chemistry, so like just ignore that. So your equation would be NH3 times H3O plus divided by NH4 plus. Yep. So you know that at equilibrium, the concentration of ammonia and your hydronium ion, or the OH minus base. Yep. So like the products would be of the same concentration to each other. So if you are having like 2 species in your products, they would be having the same concentration. And then the concentration of your reactants would be roughly the same when it was at the start and then when it reaches the equilibrium. So if our concentration for the salts was 2 molar and the concentration for H plus, which we calculated, is 3.39 times 10 to the negative 5, then like we'll just plug these values into the equation and find K and Q. Yeah, so after you got K and Q, you can start making a table. So this table is the products of H3O times the conjugate base ammonia. Yep, so I would time those 2 concentrations together, make them into 1 column, and then leave the other cation in the other column. And then I would plot that table onto Excel, and y-axis would be the products, yep. And then x-axis would be your reactants. So whichever value you get from the slope, that's gonna be your acidic dissociation constant. Yep. So just to explain it, the y-axis would be this thing up here. X-axis would be that species down here. So when you put these 2 factors into a slope, it just tells you that, hey, I'm trying to find the quotients of this equation, and it actually is a KEQ, or in this scenario, the Ka of your salts. Yeah, so just plot it, find the slope, and then compare your Ka to the calculated KEQ, and then compare the percent error of your Ka to the theoretical Ka. So like just Google up the Ka for your salt. So for example, it's ammonium nitrate. I'll just Google that and then find the percent error between the 2 values. Yes, so that is part B. Part C would be doing the exact same thing as part B, but you will be picking the basic salts instead of the acidic salts. Do the same thing again, write your hydrolysis reaction. In this case, sodium hydroxide is a strong base, right? So that will remain as sodium plus and OH minus and will not participate in your hydrolysis equation. The other anion would now become acetic acid. Yep, and then you would have the remaining OH minus bases in the solution to make the entire solution basic. So same thing, you would just go back to the simulation over here, change the type of salt. So I would just remove the probe, and then the whole list of salt would reappear again. Sodium acetate, fine. Yep. Go back to change your molarity. The volume would be 40 milliliter again. Yep, and then just insert the probe, do your recording, get the pH, do your calculation to get the H plus concentration. Use your Kw, which is 1.0 times 10 to the negative 14. Divide that by your H plus concentration in order to find the basic concentration. And then same thing again, the base concentration would be equal to the concentration of your conjugate acid. Time those two together, make it into a column, and then find the concentration of the starting material, which in this case is acetate base, like acetate ion. So form them into two columns and then make a plot to find your Kb. Because this time it's a basic salt. The slope you'll be getting would be Kb. So find Kb, calculate Keq. Yep. And then you will be comparing Keq to Ka. So in order to find Ka, that would just be like Kw divided by Kb in order to find Ka. Then you would do the same thing again, compare Ka to Keq, and then the experimental Ka to the theoretical Ka. Yep, so that is it for the simulation, 3 parts. I figure it would be easier this time than like at least like the other 2 experiments that you were doing before. All right, so moving on to like the 3rd and the 4th data table that you are assigned. After you have got all of your 3 salts done, just start plugging in the hydrolysis reaction that you have written down in your lab notebook. Make it into this data table. The other salts would be found in the class spreadsheet. so like I would have to make the class spreadsheet and then I will send that out. But if you can, like I am sure you can do that. Like just write the hydrolysis reaction yourself and note down like what is the spectator ions, and then find the value for Ka and Kb using the class spreadsheet and complete this data table. Yep. So that is just it for this experiment. I think it's actually easier than I thought. Is there anything else that I'm leaving out? I don't think I'm leaving anything out though. That was something I thought of telling you guys and I forgot. But just do the simulation and the experiment, and I will also send out an email, not email, a message telling you what I'll be looking for in the lab report. So I will reply to all of your messages and emails. I will create a class spreadsheet and assign you with the 3 salts, and then I will send out another message to show you guys what I'll be looking for to grade your lab report. So if you have any questions, yes, message me. I would try to message you back soon. I'm so sorry for abandoning all of you like the whole week. I am so sorry. So like if you need time to work on this lab report, like feel free to just use the time. Like because I'm sending out this video late night on Saturday. You would have like at least till Saturday to get this one done. So if you want to turn it in by Sunday next week, it's fine. Like I would also hold the normal lab hours on Tuesday, so that you can decide to turn like maybe both of them by next Tuesday, or like one by the end of next weekend, or like the other one by Tuesday. It's up to you. Like I just hope that we can all jump along and get through this term, because like everything is so strange now that it's all computerized. So like with that said, I would try better to be in contact with you all. Like thank you so much for your understanding. for your prayers. And I look forward to seeing you Monday for my office hours and Tuesday, Wednesday for the labs. Okay? Okay. Hold on. Let me stop sharing. Thank you so much and have a good night. Okay? I'm gonna see you next week. Bye.